This section of the book is on optimization. Back in the day, this was referred to as max-min problems, maximum and minimum problems. Optimization is the current favorite term for it. You try to optimize the value of some function by choosing the independent variable correctly. So what are examples of this? Why do these problems come up? So you might want to maximize your profit as a function of the price you charge for an item. Or you might want to minimize the amount of aluminum you use to manufacture a can. Or you might want to minimize the amount of time it takes you to travel by various routes to a certain destination. There are lots of physical problems and business problems, just lots of problems in the real world that amount to optimizing a function of a certain variable, and you want to know what value to pick for the variable to maximize or minimize the value of the function. So that's what optimization is. We have 2 or 3 different ways of approaching optimization problems. It depends on what data you're given. So let me quickly discuss kind of the theory behind it and some easy just math examples. Then we'll do 2 more complicated, more serious examples. So more real world examples. So suppose first that you've got, so this is our first case. We'll assume that we have a function f on a closed interval. And we'll assume f is continuous on that closed interval and differentiable on the open interval. Okay. What we'd like to know is, where is f biggest? How do you find where f attains its biggest value or its smallest value? Well, how do you even know it has one? We actually looked at this before. For a continuous function on a closed interval, the extreme value theorem tells you, that f does attain since f is continuous, the extreme value theorem tells us that f actually does attain a global maximum and a global minimum value somewhere in this closed interval. Okay. Great. So we know theoretically the function attains a global maximum and a global minimum value, but how do we find where that happens? Well, on the interior of the interval, so on AB, we know that if the function attains even a local maximum or minimum value, the derivative has to either not exist or be 0. We're assuming our function is differentiable, so the derivative does exist. We don't have to assume that. We could look at places where the function is not differentiable, but this is kind of the easy and the typical case. So you look at for places where the derivative is 0, so the critical points. You look for the critical points of f on the interior. Well, those are the only places that the maximum and minimum values can occur. Then you have the endpoints of the interval. You have to check those separately. Those actually are critical points because the derivative doesn't exist. And then you just make a list, a table of those values. And you, assuming you find a finite number of places where you have critical points, you make a list and you just look at what's the biggest value and what's the smallest value. So there's a quick example that I wanted to do. So a specific one. So an example of this Suppose f of x is 2x cubed minus 3x squared minus 12x. And we want to find the maximum and minimum values of f on the interval 0, 3. All right. So let's look at this. Let's look at this problem. What do you do? We're just going to make a table of x values and f of x, and we're just going to look for where f is biggest and where it's smallest. Two things we immediately throw in our table are the endpoints of the interval. We need their f values. So when x is 0, you get 0 for f. When x is 3, all right, let's see. When x is 3, so f of 3, we get 3 cubed, so that's 27 times 2, so we get 54. 54 minus, then we get 9 minus, so minus 27. So that we're back at 27, and then minus 36. So we get 27 minus 36, so we get minus 9. Okay, where else do we have to look for maxima and minima of this function? Well, at critical points that occur on the interior of this interval. So we calculate the derivative, f prime of x. We get 6x squared minus 6x minus 12. I picked this so that it did something nice. It's 6 times x squared minus x minus 2. That factors for us. So we get x minus 2 times x plus 1. Right. So we get this. For the derivative, it factors like that. So where does f have critical points? Well, you think where this is 0, so that's when x is minus 1 and x is 2. But we only care about critical points in this interval. X equals minus 1 is not in this interval. We don't care what happens at x equals minus 1. But we do care what happens when x equals 2. So the only critical point in the interior, so I should write this somewhere, only critical point of f in the interval from 0 to 3, the open interval, is x equals 2. And so we put 2 in our table, and we need the f value there. F at 2, I'll try to cram it in right here. F at 2, we get 8 times 2, so we get 16, minus 12, minus 24, so this is negative 20. Right, 16 minus 36, negative 20. So we get negative 20. So, what do we find? We just look now. The biggest value of f that we have is here. The smallest value of f that we have is here. So the maximum minimum values of f on the closed interval from 0 to 3, the maximum value is 0. So this is the maximum. So this is the maximum value. And this is the minimum value. Okay, so that's how you handle max-min problems, optimization problems on a closed interval. Of course, we didn't really have a word problem. I just stated it as a math problem in the first place. But we'll do something harder shortly. What happens if you don't have a function on a closed interval? Well, things get a little problematic in some ways. Well, actually in substantial ways. If your function is not even if your function's continuous, if it's not defined on a closed interval, then it doesn't have to attain a global maximum or minimum. The extreme value theorem does not apply. And so for a general arbitrarily bad function, we just wouldn't be able to do the problem. For one thing, there would be no maximum or minimum. And even if there were one, well, we might have trouble finding it. But there's one case that comes up often enough that it's very useful. Sometimes you've got a function that depends on a variable, and you're pretty sure that there is a maximum or minimum that you're looking for, and as this variable changes, you get closer and closer to the maximum, you hit it, and then after that you decrease the whole time. Well, that's the kind of thing that we can handle when the function increases all the way until a point and then decreases, or decreases all the way until a point and then increases. Then we don't need a closed interval. So suppose you have suppose f is differentiable on an open interval. Or it could be half open and continuous on the half open interval and differentiable on the open interval. But I'll stick with this just for ease of stating one case. Suppose f is differentiable on an open interval, AB. And that there is a C so there exists a number C in the open interval AB such that what? Such that f prime is positive on the open interval from A to C and negative on the open interval from C to B. All right. Before I say what the conclusion is, let me draw a picture of the graph. So what would this tell us? So here's some open interval. Here's A, here's B. We're not including the endpoints, A and B. We've got some number C here in between A and B. And what we're saying is f prime is positive on the interval from A to C. Well, that means a positive derivative means the function f itself is increasing. We talked about that many sections ago. So the graph, I'm just making up where it starts, but it increases. And then you reach C, and then what happens after C? Well, we're then saying that f prime is negative on the interval from C to B. Well, that means the function decreases from C to B. Well, then you attain a global maximum at C. So this is called the first derivative test. So a negative one. Then f attains a global maximum value when x equals C. Right, so this is called the first derivative test for extreme values, the first derivative test. Great. What about global minima? Well, you just change. First f would need to be decreasing, so f prime would need to be negative. And then it would need to be increasing. So f prime would be positive. F would need to be increasing, so f prime would need to be positive. Then f attains a global minimum value when x equals c. So this is the first derivative test, and it's very handy. In fact, the function doesn't have to be differentiable at c. It needs to be differentiable to the left of c and differentiable to the right. It only needs to be continuous at c, but this is, I'm stating kind of an easy form of it. So let's look at an easy example of this. Let's look at x e to the minus x. So, an example. Find the maximum value of f of x equals x e to the minus x on the entire real line. So for x in the entire interval from minus infinity to infinity. This is stated in kind of a bad way. It assumes the way it's stated, it's assuming there is a global maximum value, which doesn't have to be the case for just an arbitrary continuous function on an open interval. There's absolutely no guarantee that there is a maximum value or a minimum value. But this question is asked in such a way that if there is no maximum, if this function doesn't attain a maximum value, then this is very poor phrasing of, well, I guess it's not a question. It's a command. It's an imperative. Find the maximum value. So what do? You look at the derivative, f prime. We need the product rule and the chain rule. This is the product of two functions. Its derivative, the first thing, times the derivative of the second, plus the second thing times the derivative of the first. The derivative of e to the minus x. The derivative of e to the x is e to the x. So the derivative of e to the anything by the chain rule, you get the e to the anything back, but then you have to multiply times the derivative of the exponent. So we pick up an extra times minus 1 plus e to the minus x. You factor out the e to the minus x. You get e to the minus x times minus x plus 1. All right. We would like to know where this function is positive and where it's negative. It's a continuous function. For it to change signs, if it's positive one place and negative another place, then it would have to hit 0 in between. And so what we do for continuous functions to find where they're positive and where they're negative is we find where they're 0 and then just check the parts of the interval that we're interested in between the zeros. So where does this equal 0? F prime of x equals 0. E to the anything is never 0, so that part's not 0. This is only one time when x is 1. So, just indicate x equals 1. This is where the function is 0, so where f prime is 0. And we'd like to know whether f prime is positive or negative over here, and whether it's positive or negative over here. It can't switch signs anyplace else, because if it switched signs in between where it switches signs, it would have to hit 0, and we found the only place that hit 0. So it's either always positive over here or always negative. Always positive over there or always negative. So how do you tell what it does? You pick some value over here and you stick it into f prime and see whether it's positive or negative. So for instance, when x is 0. When x is 0, well, this part's always positive, that part's positive. So f prime is positive in this part. Put a big plus up there. When x is greater than 1, like 2, this is positive, this part's negative, positive times negative, negative. So f prime is negative over there. Great. So we know f itself, f prime was positive until here. That means f itself increases until x equals 1 and decreases after that. A global maximum occurs at x equals 1. So the global maximum, what we've just found, global maximum by the first derivative test, global max occurs when x equals 1. And that value, when x equals 1, and so the global maximum value is f at 1. F at 1 is 1 times e to the minus 1, so 1 over e. That's the biggest that function ever gets. Okay, so that's an example of how you do kind of handle max-min problems, optimization problems on intervals that aren't closed. I said that there was a third way. The third way is sometimes for physical reasons or just the way in which you're given the instructions in the problem, it's clear that there is a maximum value or a minimum value, and you look for critical points and you only find one. Well, if there's a maximum value or minimum value, it has to occur at a critical point, and if there's only one critical point, then that has to be where it is. So, for instance, in this problem, if it had been phrased differently, if it had said, determine whether this attains a maximum or minimum value, and if it attains either one of those, find those values, then we have to do all this. If what we did, so we would find the function attains a global maximum. This actually shows it doesn't attain a global minimum. It just keeps decreasing as x gets bigger. And in fact, this says as x gets bigger, f of x gets bigger. But that means as x gets smaller, as x gets smaller, f of x gets smaller. So this function doesn't attain a global minimum. But if you're told the function does attain a global maximum, so if the problem is phrased like this, it makes it clear that there is a global maximum value and you're supposed to find it. Well, we found one critical point, one place where f prime was 0, and that's at x equals 1. If we know that the function attains a global maximum, and we only find this one critical point at x equals 1, that has to be where the global maximum is. And so we could have just immediately concluded that the global max occurred when x equals 1 and done this. That's not my favorite way of doing things. It's just kind of relying on somebody giving you more information than you should have. But sometimes physically it's kind of obvious there's a global max or min, so this isn't completely awful. I'd like to look at two more serious max-min problems, optimization problems. Both of them are in terms of, money, which is something we frequently want to optimize. So let's look at kind of word problems involving maxima and minima. These are the kinds of things that actually come up in the real world where we'd like to be able to figure out the answer. So, suppose a company makes wrenches. A company makes wrenches. And it costs them an initial $10,000 to set up to make the wrenches, an initial $10,000 to set up. to make wrenches. And then let's assume that their cost is $5 per wrench to set up. And then it costs $5 per wrench for them to produce a wrench. I am not saying that this is what they charge for wrenches. This is their cost in making each wrench. And it costs $5 per wrench to make. And it costs $5 to make, let's say, it costs $5 to make each wrench. Okay, great. But then they'd like to know how much they should charge for wrenches in order to maximize their profits. And what companies do is they do market studies. And let's assume that this company did a market study and found a market study indicates that if the price of the wrench so I'll call that little p, indicates that if the price p of the wrench, so this is the price they charge, either to stores or to individuals. The price of the wrench is $5, which would be stupid for the company to charge $5 per wrench. It costs them $5 to make each wrench, and then there's initial $10,000. So it'd be stupid unless it's some kind of promotional thing and they're trying to get you hooked to buy something else. But, market study indicates that if the price P of the wrench is $5, the company will sell 200,000 wrenches. A very popular wrench. Will sell 200,000 wrenches over some period of time. So maybe this isn't a ridiculous figure. The company will sell 200,000 wrenches. But for every $10 they raise the price, so the market study also tells them, but for every $10 the price goes up, only half as many people will buy a wrench. For every $10, but every $10 that they raise the price of the wrench, only half as many people All right, a lot of words. Most real-world problems do have a lot of words in them. There's a big setup. And so the question, of course, is what price should they charge for wrenches in order to maximize their profit? So what should P be? So P denotes the price. What should P be in order to maximize the company's profit from the wrenches? All right. Great. This is our problem. So what do we need to do? Several things. The first one is, well, first, depending on how you count, or depending on what order you do things in. But I'm going to I'm going to try to come up with a formula for N of P, the number of wrenches sold when the price is P dollars. So what is this? Actually, this is a lot like, or it's exactly like, when we discussed radioactive decay and half-life, or the half-life of a drug in a person's system. You're told kind of the half price, or how much you have to raise the price by to have half as many people buying it. And it is not hard to write a formula for this. It's every time the price goes up by $10, every time the price goes up by $10, you should multiply by another half. So you want this, so that every time P goes up by $10, you'd get, so every time P goes up by $10, P over 10 would go up by 1, which would mean you'd pick up multiplying by another half. And then the question is, well, okay, so this is the thing that makes P go up, or that makes you have half as much, gives you another multiple of a half every time P goes up by 10. But we want to multiply that times what? Well, something like, we know that when P is 5, you get 200,000. So the nice way to do that is that, well, there are a couple of ways to do it. But the easiest way is to just put a minus 5 in here and then put 200,000 here. Why? What happens? When P is 5, this is 0. 1/2 to the 0, that's 1. And you'd get 1 times 200,000. Great. So we say the number of wrenches sold when the price is $5 is 200,000. Right. And then what else happens? It's still true. Every time P goes up by 10, this fraction is going up by another 1, and which means you're multiplying by another half. So this is our function. You could split off, and this is, if you prefer, you could split off. You get 200,000, and then this is 1/2. And then you rewrite, this is P over 10 minus 5 over 10. That's minus a half. So you could also write this in this form, if that looks better. But one way or the other, this needs to be the function N of P that you come up with, the number of wrenches sold when the price is P dollars. It's an exponential function with a general base of a half, and it's rigged so that when P is 5, you get 200,000, and every time P goes up by 10, the exponent goes up, this whole fraction goes up by 1, which means you're multiplying by another half, which corresponds to the every time the price goes up by $10, half as many people buy it. Okay, so we've got that. By the way, this negative 1/2, that's the same as, well, the negative sign just takes in the exponent takes reciprocal, so it's 2 to the positive 1/2. So if you prefer, you could also write this as 200,000 times the square root of 2 times 1/2 to the P, 1/2 to the P over 10. And you can also write that as N of P is 200,000 times the square root of 2. And then this is 2 to the minus 1, so you could also write, there are a bunch of ways you could write this. This is 2 to the minus P over 10. Any of these ways are fine. I think I'll stick with this one. Okay, that's N of P, the number of people who buy the wrench when the price is P. Okay, how much revenue does the company make? The revenue is how much they take in from selling the wrenches. So how much do they make on the wrenches? Well, if they sell this many wrenches and the price per wrench is P dollars, then the total amount of money they take in from selling this number of wrenches is just P times this number. So the revenue from the wrenches from selling the wrenches is just P times N of P. Right? The number of wrenches sold times the price per wrench. So this is, we take our, what we had a second ago, the 200,000 times the square root of 2. But now we have a P, and then there's times 2 to the negative P over 10. That's the revenue. But then the profit is how much money you take in minus what it cost you. And so the total profit, I'll call this T, the total profit, is the revenue, so it's this, I guess I don't need these, well, I guess I'll keep writing the parentheses. There's the revenue, and then you have to subtract your costs. Well, it cost you $5 per wrench, so that's another 5 times N of P. So you get minus 5 times, and then it's the nasty N of P function again. So 5 times 200,000 times the square root of 2 times 2, that's minus P over 10, and then minus the $10,000 fixed cost from setup. So this nasty looking function is our total profit function. 200,000 times the square root of 2 times P times 2 raised to the minus P over 10 minus 5 times 200,000 times square root of 2 times 2 raised to the minus P over 10 minus 10,000. This is the function we want to maximize. You might be saying to yourself, oh my God, that looks awful. It's not that bad. But part of the point is when you do real world problems, they look complicated because they tend to be. And this isn't even that bad a one, but it's fairly bad. But we'll make it look better. So what are we getting for our total profit? Well, of course, we could have written it this way in the first place. Go ahead and factor out, well, the N of P, really. Go ahead and factor out from here and here 200,000 times the square root of 2 times the 2 raised to the minus P over 10. And we're left, we get that. So you get 200,000 times the square root of 2 times the 2 times minus P over 10. We probably should have written it this way in the first place. You factor that out and you get the P and minus 5. So times P minus 5. And then minus 10,000. Our price, well, it could be any real number. I mean, it could even be negative. You could pay someone to take your wrenches. You're an idiot. You could pay someone. In theory, you could take someone to pay your to take your wrenches. Or you might think it's reasonable to say that, okay, P is greater than or equal to 0 or greater than or equal to 5. But certainly there's no upper bound on the price. So we are not on a closed interval. We don't know that, there's nowhere to stop P. So if we're going to succeed at finding where this is a maximum, we better be able to use the first derivative test, which means the derivative better be, and if we want it to be a maximum, the derivative better be positive for a while, then 0 or undefined, but here's 0. And then it better start, the derivative better be negative after that so that the function actually attains the global maximum. What happens? Well, let's do it. What is dp dt? dt dp. The derivative of a constant, the derivative of this part, 0. Then you've got this constant out in front, so that's not going to affect where things are positive or where they're negative. get this, but then we have to differentiate this product. And it's the product rule. It's the first thing, the 2 to the minus p over 10 times the derivative of the second with respect to p. So we pick up times a 1, plus the second thing, the p minus 5, times the derivative of the first thing. And you need to remember how to take the derivative of 2 to the minus p over 10. You get the 2 to the minus p over 10 back times the natural log of 2. Right? So the derivative of a to the x is a to the x times the natural log of a. This isn't just a p, so it's not just 2 to the p, but it is a constant raised to a variable exponent. You take the derivative, you get the constant to the variable exponent times the natural log of the base. But then by the chain rule, you have to multiply again by the derivative of this exponent with respect to p. So you pick up another times minus 1/10. All right. That's what we get for the derivative. And fortunately, we can factor out the 2 times, or 2 raised to the minus p over 10, which is always positive. So it also does not affect the sign of the derivative, so whether the derivative is positive or negative. You can factor out this 2 to the minus p over 10, this 2 to the minus p over 10, and write this nasty looking derivative as this times 2 to the minus p over 10. What are we left with? Not that much. There's a 1, and there's a plus p minus 5 times the natural log of 2 times minus a 10th. And yeah, this stuff is kind of ugly, but it doesn't affect whether the derivative is positive or negative. The derivative will be positive when the stuff in the square brackets is positive, because all this is positive. Be negative when this stuff is negative, 0 when this stuff is 0. So what do? We find where this is 0, and then we check on either side whether it's positive or whether it's negative. So you set this equal to 0, and you solve for p. What do we get? So we've got, I'll just rewrite it. You've got 1 minus p minus 5 times the natural log of 2 divided by 10 equals 0. Okay, put this on that side, multiply by 10, multiply both sides by 10, you get 10 equals p minus 5 times the natural log of 2. Then you divide both sides by the natural log of 2 and add 5, and you find that p is 5 plus 10 divided by the natural log of 2, dollars. Which is approximately, I think I wrote down what this is as a decimal. No, I didn't. Okay, I'd have to, natural log of 2 is about 0.693, but still, anyway, this many dollars. You can get out a calculator and estimate this. I could do it, but is it positive or negative when you're slightly below here and below here and above here? So you can just draw a little number line. You don't have to draw much. Here's this p-value that we're getting, 5 plus 10 over the natural log of 2. This is where t prime is 0. What we'd like to know, so here's the value of little p, and that's where t prime is 0. We'd like to see that we actually have a maximum occurring at this price. To know that, you would need to have the derivative be positive before here, so the function t itself increases until here and then decreases after there. So we need positive here, negative here. Is that really what we get? Well, you could plug in most anything down here, like in particular 5 is over here. 5 is over here because 10 over the natural log of 2 is certainly positive. And when you put in 5, all of this is 0, and you get 1. All we care about is that that's positive. So yes, T prime is always positive over here. What do you get when p is greater than 5 plus 10 over the natural log of 2? Like what? Like how about 500 trillion? When p is 500 trillion, this is huge, huge and positive, but then you multiply it times this, something huge and negative, plus 1, still negative. So yes. Right, t prime is positive over here, 0 here, negative there. T itself then increases until here and starts decreasing after that. The first derivative test tells you we have a global maximum occurring at this price. This is what they should charge, rounded to the nearest penny. All right, or up or down a penny, one or the other. Okay, that's what we get for this problem. I want to do another very different feeling optimization problem, but again, having to do with money. So let's, we could phrase this one differently. We could, or not phrase it differently, change the problem slightly and have it be about surface area instead of about money. But let's talk about aluminum cans. Aluminum cans, frequently the top and bottom are made of kind of thicker or different looking aluminum. Aluminum that looks like it might be more expensive, or it's gone through some processing that changes it, or there's some molding on the top and bottom that changes the cost of the top and bottom. So we're going to assume that, so here's another example. So we're making an aluminum can in the shape of a right circular cylinder of some radius r and some height h. And we want our can to hold, we want the volume, we're going to specify the volume that we need for it to hold. The volume V should be 500 cubic centimeters. That's 0.5 liters, but I don't care that much. Suppose that the sides of the can, so the side, this cylindrical side, so the side, it's a cost, let's just say C dollars per, cost C dollars, where C is some constant greater than 0. C is greater than $0 per square centimeter. Yeah, in fact, the aluminum has some thickness, but it's some finite, very small thickness, and I didn't mean finite, some uniform, very small thickness. And so really we talk about the cost per square centimeter, even though really there's some volume. I mean, it's definitely cubic centimeters, but you really don't, for all intents and purposes, you don't see the thickness. And then, but let's assume the top and bottom are twice as expensive. So top and bottom cost $2C, so twice as much as the sides per square centimeter. The question, what should R and H be to minimize the cost of making the can? So what dimensions should the can have to minimize the cost? What should R and H be to minimize? The cost of making the can. All right, let's do it. So you do have to know about the volume of a can in terms of its radius and height, and the area of the sides and the area of the top and bottom. So the volume, we're told it's fixed. We want it to be fixed. I'm going to drop the units. They're all the length units are in centimeters. So we want 500 to be the volume in cubic centimeters. So that, but what is the volume? It's the area of the base times the height the base is a circle of radius r, its area pi r squared, and you multiply times the height. So we get that this has to be satisfied. What this means is that r and h are not free to vary independently. We can't just change r and h any way we want. We can change r any way we want, and that'll determine h. We can change h any way we want, and that will determine r. But we can't just change r and h independently because this equation has to be satisfied. This is frequently referred to as a constraint on the variables. It constrains how they can vary. All right, so we've got that. This is not what we're trying to maximize or minimize. This is just some piece of data that we're required to satisfy. The can holds 500 cubic centimeters. Okay, but what are we told? We are told the cost per square centimeter of the sides and the top and the bottom. So the cost of the sides well, that's the cost per square centimeter times the number of square centimeters. So that's the cost per square centimeter is just C, the cost of the sides. The area of the sides, it's the area. So we've got this can. We want the area of this side, but that's the circumference of a circle times the height. So that's 2 pi r h. So that's the cost of the sides. The cost of the top and bottom is the cost per square centimeter times the height. That cost is twice as great per square centimeter, so we get 2c times, and then the area of the top and the bottom. Well, they're both circles of radius r, so each one has area pi r squared, but then we've got two of them, so you get this. So the total cost of making the whole can is, well, it's this, so that's 4c pi r squared, plus this, which is plus 2c pi r h. So there's the cost of making the entire can in terms of r and h. It looks like the cost is a function of two variables, r and h, and it is, but this is not a multivariable calculus course, and we need a function of one variable, but we have our constraint that we haven't used, and we can solve for h in terms of r or r in terms of h. I'll solve for h in terms of r, plug that in here, then we'll get the cost as a function of one variable, and we can take the derivative, find the critical point, see where the derivative is positive, negative, and do this problem. So we do that. We use the constraint and rewrite h in terms of r so that we can write our cost function just as a function of the radius. So we have, we have pi r squared h equals 500. And we have the function that we're trying to minimize, namely 4c pi r squared plus 2c pi r h. We solve this equation for h in terms of r, so it'll just be 500 over pi r squared. And then you put that in right here for h. That's the only place you see h in the formula for c. So we get c, just as a function of r, is 4c pi r squared plus 2c pi r times, and now this, so times 500 divided by pi r squared. Okay, so what happens? Well, let's see, this pi cancels that pi. You can cancel one of these r's with one of those r's. So just erase that. So we end up with c as a function of r is 4c pi r squared plus, okay, we have a 2c So we get 1000c, 1000c, everything else canceled except over r. So I'll write that as 1000c r to the minus 1 so that we can use the power rule easily. 1000c r to the minus 1. That's what we find. Yes, I have c in this problem twice. Maybe it's bad to call the total cost. I meant for this to be a capital C and that to be a little c, but they're hard to distinguish. So let's make this the total cost, and let's call this capital T. Sorry if that was confusing. We'll make this a capital T, a capital T, a capital T. Right, just in case my capital C's and my little c's weren't distinguishable. So we would like to maximize or minimize this function. This is the total cost. We're trying to minimize the cost. So what do? We take the derivative. And we want to know, well, where this is positive and where it's negative. So we'll find where it's 0 first. We can factor out the c. For that matter, we can factor out 4c. And then you get a pi times the derivative of r squared. So you get a 2 pi r. And then plus, I factored out a 4c. So I'm left with 250 times, and then the derivative of r to the minus 1. That is minus r to the minus 2. So this is what we get for the derivative. Where does it equal 0? So we need for this to equal 0. So we would need, I think I'm going to fit this right here, we need 2 pi r to, so there's a minus 250, and then minus 250, r to the minus 2, that's over r squared. We want that to be 0. So put this on the other side of the equation. So we need 2 pi r to equal 250 over r squared. Multiply both sides by r squared and divide by 2 pi. You get r cubed should be 250 over 2 pi. That's 125 over pi. 125 is a perfect cube. It's 5 cubed. So this says that r should be 5 over the cube root of pi. Centimeters. So all this is in centimeters. That's what we find is the only critical point. And if the cost, if there is a minimum cost of making the can, it will occur when r is 5 over the cube root of pi. And now you kind of have a choice. Either you just assume it's intuitively obvious from the physical setup that there's a lowest price for making the can. That is kind of intuitively obvious, in which case it has to occur there. Or you actually use the first derivative test and you look at, so here's, we want a little number line to indicate whether dt dr is positive or negative. And here at 5 over the cube root of pi, we're getting 0 for the derivative. The question is, what happens when r is smaller than this, and what happens when r is bigger than this? When r is smaller than 5 over the cube root of pi, what's something smaller than 5 over the cube root of pi? Well, 1, for instance. If you let r be 1, well, maybe it's not obvious that that's the cube root of pi. Pi is about 3. The cube root of pi is slightly greater than 1. So certainly 1 is smaller than this. So when r is 1, you get 1 squared, or 1 to the minus 2, so that's 1. You get minus 250. So you get 2 pi minus 250. That is certainly negative. So dr dt is negative over here. When r is bigger than this, what's an r that's bigger than this? 300 trillion. When r is 300 trillion, this is r to the negative 2. That's 1 over r squared. When r is 300 trillion, this is very close to 0. And so this is very close to 0, but this is very big. So certainly this is positive. So yes, by the first derivative test, we see that, in fact, we do have a global minimum occurring here because dr dt is negative, which means t decreases until here and then increases after that. A global minimum occurs here. So this r equals 5 over the cube root of pi is an r, is the r, at which the total cost of the can will be a minimum. We're actually asked to find the dimensions. So what are r and h? So we need r equals what we just found, 5 over the cube root of pi centimeters. What does that make h? Well, you plug that back in here and you solve for h. Notice that c, the cost per square centimeter of the sides, does not enter into this. This is where, I mean, it will affect the cost of the can, but the dimensions of the can at which that minimum cost occurs do not depend on what c is. So here's r. What's the corresponding h? You use your constraint again. You had this, and so you get 500 pi. You take this squared, so this is 5 squared is 25. This is the cube root of pi, that's pi to the 1/3, but now we're squaring it, so we get pi to the 2/3. 500 divided by 25 is 20. And then you get pi divided by pi to the 2/3, but that's pi to the 1/3. It's the cube root of pi again. So you get the cube root of pi here also. And this is centimeters. So this is h. You can see that h is 4 times the radius. Or what's the same thing? 2 times the diameter. We would need h would be twice the diameter, which is kind of roughly how most aluminum cans look. Saying it this way, the kind of relative dimensions of the can, the ratio of the height to the radius, that gets rid of the 500. You can do it as an exercise that regardless of what you pick for this volume, we pick 500, that if you find the dimensions of the can that minimize the cost, it will always be that h is twice the diameter, regardless of the volume of the can. All right, those were fairly difficult optimization problems. Optimization problems, in general, the word problems tend to be slightly difficult. Word problems frequently are, and problems that apply to the real world are frequently more difficult than these made-up, easy little math problems like here's a function, maximize or minimize it on this interval, because a big part of the problem is to translate the physical situation that you're given into a math problem. That translation is called modeling. You're taking this real-world problem and modeling it by this math problem that strips away all the words and just leaves you with an equation to differentiate, and maybe some constraints, so some equations. Anyway, you won't get good at these without trying them, so you need to do a bunch of these exercises.